Parallel lines. Consider a plane. Now consider a line in that plane. Now consider a point on that plane not on the line. Can you draw another line through that point that never intersects the given line? 2 different lines. 3 different lines. The answers to this are known as parallel postulates, and there is more than one. For reference, the angle between 2 coincidental lines is an empty angle of measure 0. Angles less than a quarter turn are acute angles with measures between 0 and 90. An angle of a quarter turn is a right angle measure 90. Angles more than a quarter turn are obtuse angles with measures greater than 90. When the lines are end to end, halfway around, it is called a straight angle with measure 180. A straight angle is also equal to 2 right angles. Angles can continue a full turn back to the beginning. The full turn is 360. However, these angles greater than 180 will not be used. Angles are measured in various other ways. This method is inconvenient in trigonometry, but simplifies basic geometry. Consider 2 lines P and Q. Add a third line S that intersects both. Line S forms 4 angles with both given lines. The angles between P and Q on the same side of S are called the interior angles. The angles on opposite sides of S are called the alternate angles. Alpha and beta are interior angles. Alpha prime and beta prime are also interior angles. Alpha prime and alpha are alternate angles. Beta prime and beta are the other alternate angles. Also, the intersection of 2 lines had 4 angles. The 2 angles across from each other are the vertical angles. Delta and delta prime are vertical angles, and epsilon prime are also vertical angles. When angles lie along a straight line, they add to 180. This means epsilon and delta, sharing line Q, add to 180, and epsilon prime and delta on line S are also 180. We combine these, and delta drops out, resulting in equal vertical epsilon equals epsilon prime, and in the same way, delta equals delta prime. We add a 4th line T that intersects the other 3 so that lines Q, S, and T intersect at one point. This produces a triangle between P and Q. The interior angles of the triangle are alpha, beta, and gamma. The obvious answer to the question of how many parallel lines is that there is one and only one parallel line through the point. It was so obvious mathematicians spent 2,000 years trying to prove it, but it stubbornly refused all attempts to prove from other postulates, so mathematicians since Euclid had to include it as its own parallel postulate. Euclid's parallel postulate is that 2 lines P and Q are parallel when they are crossed by another line S and the sum of the interior angles are 180, that is alpha plus beta is equal to 180, and as well alpha prime plus beta prime is equal to 180. An equivalent parallel postulate is Playfair's axiom that given a line P, a point not on P, there is one unique parallel line Q. In Euclidean geometry, alternate angles are equal. We use the postulate that interior angles sum to 180 and the angles sharing P, or Q, also sum to 180. We pivot around the common angles to equate the alternate angles. Returning to the triangle formed by lines P, S, and T, the angles along Q at the peak of the triangle have to equal 180, and we have shown these angles equal the angles of the triangle. The sum of the interior angles of a triangle is 180. To understand the other parallel postulates, first look at some models to base geometry on. These models are quadric surfaces in 3-dimensional space and the intersection of lines in planes of 3 space with these quadric surfaces. A quadric surface is defined by an equation where all the terms are at most quadratic, at most a power of 2. A wide variety of surfaces can be specified as quadrics. 3 in particular are the sphere, 2 quadric planes, and a hyperboloid of 2 sheets. Every line through the origin of 3 space can intersect each of these surfaces twice. I will call these oblique planes, planes through the origin except for the vertical plane z equals 0. I also call the line intersections of the oblique planes oblique seams. Because all the oblique planes pass through the origin, all the oblique planes must intersect, resulting in the seams. Where a oblique plane meets a quadric plane is a straight line, where the oblique seam meets a quadric plane is a point. Moreover, just as the seam is the intersection of two oblique planes, and its point on the quadric planes is at the intersection of the lines. When an oblique seam does not meet a quadric plane, the oblique planes do not intersect in the quadric planes. The oblique seam not meeting the quadric planes is the same as the oblique planes making parallel lines in the quadric planes. Note that an oblique seam never meeting the quadric planes forces the seam to lie in the vertical plane z equals 0. Also note that a third oblique plane to the parallel creating planes makes seams with both, and both seams inevitably cross the quadric planes. Where an oblique plane meets a quadric sphere is a great circle, and where an oblique seam meets a quadric sphere is a pair of points which are the two ends of a diameter. Because the sphere completely surrounds the origin, all oblique planes and thesemes must intersect the sphere's surface. Following what is true for quadric planes, when a seam intersects the surface, the traces of the oblique planes, the great circles, on the sphere must intersect each other. If we let great circles on a sphere be the same as straight lines in the quadric planes, no great circle has a parallel in the quadric sphere. This will be a model for the no parallel postulate. Last is the quadric surface is the hyperboloid. Where a oblique plane meets a quadric hyperboloid is a hyperbola, where the oblique seam meets a quadric hyperboloid is a point in each sheet. When an oblique seam does not meet a quadric hyperboloid, the oblique planes, and the hyperbolas they trace, do not intersect in the quadric hyperboloid. The hyperboloid is an asymptotic surface. It is completely contained in a double cone. It comes closer and closer to the cone but never reaches it. The space outside the cones is much more expansive than between the quadric planes. This allows seams in more directions for a seam which still misses the hyperboloid surface. As with quadric planes, oblique planes whose seams do not touch the surface means their hyperbolas will never intersect. These hyperbolas are parallel. If we let the hyperbolas on a hyperboloid be the same as straight lines in the quadric planes, a hyperbola has many parallels in the quadric hyperboloid. This will be a model for the multiple parallels postulate. Insisting a parallel line must mean a straight line is forcing everyone to play by Euclidean rules. Instead, we generalize a straight line to a geodesic. Informally, a geodesic is a path on a surface where you travel always one foot in front of the other, never stepping to the left or right. A person traveling a geodesic would see themselves as traveling in straight, but someone looking down on the path would see it curving where the surface curves. We can travel along one of these geodesics on a sphere. Note that the geodesic we are following appears straight, deviating neither left nor right, while another geodesic appears to be curving around us. When we switch to the other geodesic, now it appears to be straight and the geodesic we left appears to be curved. It can be said these lines are not really straight because they are bending over the horizon. This is because our vision is not restricted within the surface, but looking down on the surface from above. If we confine our vision to follow the surface, it now appears we are traveling a flat plane, following a straight line. The curvature is not part of the geodesic, but part of the surface, whether we can see the curvature directly or we must infer it from the behavior of the geodesics. When we are traveling on a hyperboloid, the geodesic we are following again appears as straight, while other geodesics appear curved. However, on the hyperboloid, intersections are not inevitable, and we can have a parallel line, and even multiple parallel lines. When we move to one of the parallel lines, it changes from curved to straight while the original geodesic is now curved, and switching at an intersection. And again we can remove the explicit curvature of the surface and make it appear to be a flat plane with implicit curvature. These surfaces and their geodesics are models to inspire the geometries to follow, where the surface illustrate a plane with curvature, and the geodesics, lines. The geometry is not of these surfaces, but the surfaces are useful to check our intuition. Some of these geometries can have other models. In 2 dimensions, a smooth curved line matches a tiny arc of a circle at each point, with the circle's radius varying as to how tightly the line curves. The curvature is the inverse radius of this matching circle. The smaller the curvature, the flatter the curve. A straight line matches a circle of unbounded radius, so its curvature is 0. The curvature of a circle is the inverse of its own radius. The smaller the circle, the larger its curvature. In general, the curvature is defined by the first derivative and second derivatives. Here is an example of a one-dimensional curve and the curvature as we travel along it. The blue circle is the tangent circle whose inverse radius is the curvature at that point. The tangent line, or first derivative, is in red, and the normal, or perpendicular to the tangent, is in green. The second derivative is in yellow. The curvature is shown by the circle. To illustrate their connection, they are all drawn at the point of the function being examined. The curvature can be positive or negative. Using this orientation, positive curvature is where the function is like a cup opening upward, and negative curvature where it is kappa opening downwards. Which direction is positive or negative is arbitrary, as long as the orientation is consistent. Curvature is extended to 2-dimensional curved surfaces. These images are surfaces embedded in 3-dimensional Euclidean space. In this case, curvature is based the tangent plane in red and the normal vector in green. The surface has 2 principal curvatures in perpendicular directions. The overall curvature is the product of the 2 principal curvatures. Again, the principal curvatures can be positive or negative and can vary with the observer. However, as negative times negative is positive, and negative times positive or positive times negative are both negative, their product is stably positive or negative. This product is shown as a blue, positive, or red, negative, sphere. This product curvature is related to Gaussian curvature. Gaussian curvature is defined from the surface itself rather than surfaces in 3-dimensional Euclidean space. The significance is that in surface with negative Gaussian curvature, a geodesic can have multiple parallel geodesics, but with positive curvature, no parallel geodesics. Thus, the Gaussian curvature of a model surface determines the geometry within the surface. Conversely, the geometry of a surface determines its curvature. Note that for a 2-sheet hyperboloid, the product curvature is positive but its Gaussian curvature is negative. A surface, such as a plane, has 0 curvature. A surface with 0 curvature with Euclidean geometry where a geodesic has 1 parallel. As a blue sphere's diameter increases, its curvature in yellow decreases. A portion of the sphere's surface becomes more plane-like. The limit as the radius increases without bound, its curvature goes to 0 and its surface becomes a plane. Where the curvature of an object is 0, it is also said to be flat. In this context, flat just means 0 curvature. It does not mean the space is 2-dimensional, nor that it is horizontal, nor that it has no relief. One way to determine the curvature of a surface is to draw a triangle on it and sum its interior angles. As already shown on a flat surface with Euclidean geometry, the sum is always be exactly 180. With positive curvature it is called elliptic geometry. The sum is always greater than 180, but negative curvature is called hyperbolic geometry, and the sum is always less than 180. Inspired by the sphere model, we can derive what is called elliptic geometry by assuming a parallel postulate that there are no parallels, or lines intersect. When we project this onto a plane, the lines appear to be curved, but the curvature is in the surface, not the lines. Before addressing triangles, a few preliminary theorems. First is that all perpendiculars to a given line intersect at one point, called the pole of the line, and that each perpendicular has the same distance, the polar distance to the pole. Because all lines intersect, add two lines at any angle to a baseline and the lines must intersect. So we add them at right angles to the base. The equal base angles and inevitable intersection at the pole means we have an isosceles triangle, and the sides of an isosceles triangle have equal length, the polar distance. So both lines have the same length from the base to their intersection. We will call the distance between the lines at the base as 1. The actual distance is not important except we want to construct triangles with the same length base. We add a third perpendicular that must intersect the line next to it with the same base length and base angles. This makes the triangles congruent, thus the same pole and polar distance. This can be replicated with all perpendicular lines at an integer distance intersect at the same pole and distance. Now construct the triangles with a base length of 1/n. All of these triangles have the same pole, but perhaps it is different than the integer distance triangles. But no, the fractional base reach the integer distance triangles, thus the small base and integer base triangles all have the same pole. This makes sense since the distance of one was arbitrary. All rational distances have the same pole. Using Cauchy limits, this generalizes to all real number distances. All perpendiculars to one particular baseline have the same pole and polar distance. Now we that each baseline has a pole and its polar distance is the same. Each line has its own pole, but all lines have the same polar distance. We do this by constructing an isosceles triangle with the same base length and base angles as the original. Again, the sides must intersect somewhere because all lines intersect. The isosceles triangle on the new baseline is congruent to the original triangle, thus the lengths of the sides are equal. From this first triangle on the new base, we can repeat the preceding to show every perpendicular has the same pole, and, despite being a different line and pole, the same polar distance. Next, consider the relation between an angle of a right triangle, alpha in this diagram, and the length of the opposite side, A in this diagram. Sides A and B are the legs of the right triangle, and C is the hypotenuse. A perpendicular where the angle alpha will have the same pole as side A if alpha is acute. The hypotenuse is less than the polar distance, making where it meets side A also less than the polar distance. When alpha is also a right angle, the hypotenuse intersects the leg at the polar distance. The length of A is the polar distance. Finally, for an obtuse angle, the hypotenuse meets the leg beyond the pole. The length of A is greater than the polar distance. Now we can prove the sum of the angles in a right triangle is greater than 180. In the first case, let the leg A length be at least the polar distance q. This case is straightforward. The opposite angle alpha must be at least 90, 90 plus the non-zero third angle, however small, total to over 180. In the second case, neither leg of the right triangle has least the polar distance q. This implies both of the interior angles are less than 90. We have to show that despite this the sum is greater than 90. The strategy is to construct a larger triangle, one of whose interior angles is this sum alpha plus theta, and the constructed side opposite is longer than the polar distance. Add a perpendicular to leg A that passes through the midpoint D of the hypotenuse. Being a perpendicular, the line with leg A has a pole at the polar distance. We extend this constructed line to a point F such that the distance from D to F or E is the same. Note that at this, besides the original triangle, we have two smaller triangles on the midpoint of the hypotenuse, BDE and DFA. We will use the smaller triangle to find what is happening at F. These small triangles were constructed on the hypotenuse midpoint, and with the other sides DE and DF, they also share a vertical angle, which must be equal. Thus the small triangles are congruent. The corresponding angles are equal. Thus FA is perpendicular to FD, and the angle between AF and AD is beta. This gives us a shared angle between AF and side B with the desired angle sum alpha plus beta. Finally, FP and EP on the same base intersect at the same pole. This make FP another perpendicular on base FE. The sum of the angles on other side of F is 180. P, F, A are collinear, making PAC one big triangle containing the other triangles. Looking at this big triangle, the base angles alpha plus theta and the original right angle, the side opposite alpha plus theta is the polar distance PE plus whatever is left under EC. Thus alpha plus theta is at least 90 because the opposite side is at the polar distance. Together with the third angle at the pole, we have alpha plus theta plus 90 plus the pole angle is greater than 180. The sum of interior angles of a right triangle is therefore always greater than 180. Now to show this for in triangles. If the triangle has two right or obtuse angles, it is immediately true. The last case is when the triangle has two acute angles. The given triangle is split into two right triangles by a perpendicular to the base through the remaining angle. Being right triangle, their sum exceeds 180. Recombining the split angles gives the desired result. Now, inspired by the hyperboloid model, we can derive what is called hyperbolic geometry, this time by assuming a parallel postulate that there are multiple parallels. Consider a triangle in the hyperbolic plane. First is the exterior angle theorem. When one of the sides of a triangle is extended, it forms an angle between the base and side that is outside the triangle. The theorem is this angle is larger than the other two opposite angles. We proceed by constructing a triangle that is able to bring the exterior angle and an interior angle into direct comparison. Through the midpoint of an adjacent triangle side, constrict a line that both bisected and bisected. Adding the third side, we have divided the original triangle in two as well constructed a new triangle. Two of the triangles are congruent. This allows us to bring the interior angle inside the exterior. Note that for beta to equal delta, the line AF would have to lie on the baseline B, or side A has zero length. By a similar construction, the exterior angle can be compared to the other interior angle. A line has at least two parallels through another point. Draw a perpendicular vertical line to that point. Intersecting and parallel lines through the point are on either side of the vertical line. The intersecting lines are through the whole of the base, forming an open set. Their complement, the parallel lines, are a closed set with minima in the set. These minima are called the left and right parallel. These are the only parallels that will be distinguished. The existence of the other parallels is significant, but not their identification. These other parallel lines are sometimes called non-intersecting rather than parallel, and the word parallel is reserved for the left and right parallels. The left and right parallels are asymptotes. They come closer and closer to the baselines but never actually intersect as you go infinitely far out. The angles between the two parallels and the vertical are equal acute angles. This angle is called the parallel angle. It turns out the parallel angles are the same for all lines, depending only on the distance, but this will not be used. The proof the angles are equal and acute starts with a false assumption they can differ until it contradicts itself. This leaves space on the alpha side alpha prime and a bit more. Construct a line at this angle. Because it is less the left parallel angle on the left side, it must intersect the baseline. Mark the intersection and the distance from the perpendicular. At the same distance on the other side of the perpendicular, draw another line. Because both constructed triangle are right triangle with the same vertical leg and other legs, the triangles are equal. Thus the angles at the peak are equal. Thus the rightmost side cannot intersect the base because at that angle it must be the right parallel. The assumption the angles differ is rejected. Now falsely assume the parallel angle is 90. This makes the left and right parallels, and all other non-intersecting lines, collinear. This violates the parallel postulate of multiple distinct parallels. Finally, falsely assume the parallel angle is obtuse. We can then construct an intersecting line perpendicular to T, but this line must be parallel, contradicting the assumption. Next we will show that we can connect two lines with a third line that is perpendicular to both. At the moment lines A and B are presented as two separate lines. We can construct a perpendicular from each line to the midpoint, but we do not yet know the relation of the two perpendiculars. Construct the two right triangles with the given line as their hypotenuse. Their hypotenuses are equal. They share the same angle beta. They are congruent triangles. This makes the remaining interior angles equal. This makes them vertical angles and A and B are collinear. Thus we can construct a line which is mutually perpendicular to two given lines. We also get a corollary when a line crosses another. Zachary was a mathematician who attempted to prove Euclid's parallel postulate. Instead, he discovered hyperbolic geometry, but rejected its counterintuitive results. The hypothesis of the acute angle is absolutely false, because it is repugnant to the nature of straight lines. We now consider the Zachary quadrilateral. It is built on a baseline with two sides of the same length perpendicular to the base. The fourth side is the summit. The question is, what are the angles between the summit and sides? In Euclidean geometry, their sum is always 180. In elliptic geometry, their sum is always greater than 180. We want to prove the summit angles are equal and acute. Given two lines, construct two more lines of equal length between them that are perpendicular to the baseline. Many proofs in this section create congruent triangles to move a line segment or angle from one place to another to show a comparison. First, add diagonals to the quadrilateral to divide into four overlapping triangles. We use the two lower triangles to equate the diagonals. They are right triangles with equal base and altitude lengths, making them congruent. That makes their hypotenuses, the diagonals, equal length. Now the upper triangles have sides of equal length, making them equal. That makes their angles equal, especially the top angles alpha and beta are equal. The top two angles are equal. Now to prove the angle alpha is acute, we add the right parallels and the equal parallel angles. We construct what is called an omega triangle, a peculiarity to hyperbolic geometry. It is triangle with one corner stretch out an infinite distance. Without proof, an omega triangle can be treated as a limit of a triangle with an interior angle of 0. In particular, the exterior angle theorem is true for omega triangles. We have the exterior angle theorem, the sum of angles on a line equal to 180, and parallel angles to get enough relations involving alpha to restrict the range of alpha. Alpha is an acute angle. Now that we have a Zachary quadrilateral, we cut it half. The midpoints of the summit and base of a Zachary quadrilateral are joined by a line perpendicular to both. We join the midpoint of the top to the midpoint of the base. This cuts the Zachary quadrilateral into two contained quadrilateral. We add the diagonals to get two right triangle with equal length sides and equal length halves the base. These triangles are congruent, which means their hypotenuses, the diagonals, are equal. That diagonals created two more triangles, each sharing the midpoint joiner, with two equal halves of the top and two equal diagonals. That makes these inverted triangles also congruent. Thus the two angles on either side of T, gamma, are equal. Gamma plus gamma on a line makes gamma equal to 90, and all these congruent triangles makes the pair of angles at the bottom of T also 90. T is perpendicular to the top and bottom sides of the Zachary quadrilateral. Half of the Zachary quadrilateral, split by the perpendicular bisector, is another quadrilateral, called a Lambert quadrilateral. Three of the angles are right angles. The remaining angle is the summit angle of the Zachary quadrilateral and acute. The purpose of the Lambert quadrilateral is that we can construct one on a right triangle such that the summit angle, which is acute, is equal to two of the right triangle interior angles. Next, consider a right triangle. The sum of the interior angles of a right triangle will be shown to be less than 180. Construct a perpendicular from the base to the hypotenuse midpoint. Above the hypotenuse, construct another triangle with a copy of the distant interior angle, and side equal to the divided base. We do not yet know the relation of FQ to QD or the other angles of new triangles. However, the two sides equal by construction, the two halves of the hypotenuse and the equal angles by construction, the triangles are equal. This makes the corresponding angles equal. ADQ and BFQ are right triangles and the angles around the midpoint Q are equal. FQ and QD are collinear. The quadrilateral FBCD is a Lambert quadrilateral with three right angles. The remaining angle, alpha plus beta, is acute. The sum of the interior angles of the original triangle, alpha plus beta plus 90, is less than 180. As with elliptic triangles, a hyperbolic triangle can be divided into two right triangles. The sum of angles of the right triangles is less than 180. Recombining the right triangles and the sum is still less than 180. The sum of the interior angles of a triangle in hyperbolic geometry is less than 180.
Euclidean world of Minecraft, this is a negatively curved space. So to illustrate this negative curvature, I'm going to walk around this pillar to my left. And to get our bearings, this cube that I'm starting in has this sphere down here, and there's the red light ahead of me, and there's a blue light to my right. So let's get going. So this world is curved, a little bit like how space is curved near a black hole. Light rays travel along strange curved paths and so on. And so there's going to be a mismatch between where I end up in the real world and where I end up in the virtual world. So I'm now back where I started in the real world, but you can see that where I started in the virtual world is one cube further in. There's the sphere and there's the red light there. So rather than walking around the sides of a square to get back to where I started, I have to walk around the sides of a right-angled pentagon. The code is also available on GitHub. Thanks for watching.
Thus, the parallel postulates of the geometry of a space correspond to the curvature of that space, and curvature is not something that has to be observed from above or outside. The curvature is intrinsic to the space and be measured by measuring triangles, or circles. From the triangle theorems we can derive that for circles in Euclidean space the circumference is exactly 2 pi times the radius. In elliptic space the circumference is always less than 2 pi times the radius, and hyperbolic space greater than 2 pi times the radius. We also do not have to assume a space must have only one curvature and one kind of geometry. We can divide the space into small patches and each patch has its own geometry.